Yeah, it would be. Sometimes, like, my laptop camera, like, you know how, like, in the phone, like, you have to look at, like, the actual thing, but, like, in a laptop, it's not. It looks like you're not looking at the person.
Well, this is going to be a nice, easy day today. Nice and, we'll take our time.
Are we going to have a test this week?
Next week.
Oh, gosh.
You want one?
Yeah, I'm fine, thank you.
You're good. No, next week. So, speaking of, I mean, I still need to let the other classes know, but since she brought it up, we're getting towards the end of the unit soon. Okay, we're gonna start a section today, and then our last section will probably be on Thursday, which means next week you'll have partner quiz and unit test. So, for some of you, I don't know how you're going to view it, but we are going to get in the partner quiz and the unit test before the end of the quarter. So for those of you that are kind of borderline close in terms of a grade that you really want, this is going to be good for you because you have these opportunities to change that. Okay? So we are going to get it in before the end of the quarter. All right, so yesterday we were looking at symmetry in terms of a graph, how we can either rotate a graph upside down and it would be the exact same picture, or you can fold a graph somehow and it would line up on itself. We're going to take a look at two specific types of symmetry today. I know we did 4 yesterday. You had the origin, the y-axis folding, the x-axis folding, and then the diagonal folding. Okay, of those 4 from yesterday, we're only really going to look at 2 today, 2 special ones in this section. So what we're going to do is try to classify these graphs. We did a few of these yesterday. If you take a look at f of x, would you be able to flip that graph upside down and it would be exactly the same? Or can you fold it somehow that it would line up on itself? Can you describe the symmetry? Yeah.
Fold it over the y-axis.
Okay, so this is going to be a y-axis fold. So that's where our crease or imaginary line would be if we were to fold the graph. And if we can fold a graph, that's described as reflective symmetry. What about g of x? Can you rotate that graph or can you fold that graph? Yeah.
Rotate.
Or rotate it. So this would be rotational. Sometimes we call this origin symmetry because we're keeping that origin point still. Like if you were to put your finger there and press down and rotate the paper, okay, it would produce the same graph. What about h of x? Can you rotate it or fold it? Yeah.
Rotate.
Rotate. So there's another origin symmetry. What about p of x? Bless you. Can you, yeah.
Fold over the y.
All right, so we have another y-axis. Okay, so that's reflective. All right, what about r of x? Rotate it or fold it? Yeah.
Rotational.
That's a rotational. Yep. Sometimes you have to actually flip it to see it. Some of them are easier to see than others. And what about q of x? Rotate or fold? Yeah.
Fold.
Fold again. Okay, so reflectional or reflective. And where can we fold it?
On the y.
The y-axis. Okay, so if you haven't noticed already, the 2 types of symmetry that we're going to focus on in this section are the origin. Okay, if you were to rotate it, but also the y-axis folding. Okay, we have these two particular types that are a little bit more important, or at least we can investigate them a little bit further. So what I need you to do is take that paper out of your binder. If you have it in there, we're going to do some flipping back and forth. On the next page, we're going to identify, or we already identified, but we're going to list those y-axis graphs that we identified and those origin graphs that we identified. So on the front page, notice how the y-axis functions were f of x, p of x, and q of x. So in our y of x table, or y-axis table, we're going to label f of x, p of x, and q of x. Now in the big sections on that chart, I want you to write in the ordered pairs from the table or from the graph on the other page. So for instance, if you look at the f of x graph, the first point I kind of stress on there is -4, 1. The next point is -2, -1. So I want you to go ahead and write those ordered pairs in this block. Okay, you read a graph left to right, so go ahead and write in those ordered pairs the same way. Do you guys think you can fill out the ordered pairs for those three functions? Okay, work left to right. Alright, when you guys get done with the y-axis table, can you move on to the origin? Those are the other three graphs that we talked about. G of x, h of x, and r of x. Go ahead and write down the ordered pairs from those ones too. We're writing them down because we're eventually going to want to try to find a pattern. Okay, a connection between all these numbers that have origin symmetry and y-axis symmetry. All right, the ordered pair is ready to go? All right, so on the next page, 101, we have these two questions at the top. Okay, what observations can you make about all the points on a graph that have y-axis symmetry? And what about all the points on a graph that has rotational symmetry? So we're going to analyze these ordered pairs, and whatever observation or conclusion we can get from the relationship here, we're going to write them down on page 101. So go ahead and let's take a look at the y-axis ordered pairs first. Can you find a connection between the numbers or the ordered pairs for each individual function? Do you see a pattern? We got nothing? Can't see anything? Yeah.
All the Y's obviously, or like the opposite ordered pairs.
Okay, so what do you mean by opposite ordered pair? So if let's say I choose this point, what do you mean by opposite ordered pair?
The 4, 1.
4, 1 down here. Okay, so the y value stays the same, and what else did you mention?
The x values are opposite.
The x value changes, okay? So let's see if that holds true. If I were to pick another ordered pair, the, I guess, opposite or connected point would have the same y value, but an opposite x value. What if I were to choose this one? We don't really have a connected point for that one. Why not? Yeah.
It's the vertex.
It's the, what do you mean by vertex?
The orange.
It's, okay, it's not necessarily at the origin, because origin is 0, 0, right? Where is this point located on the graph? Maybe reference on the other page, 0, -3. Where's that located on the graph? Give me a look. 0, -3. So it is the vertex of this V shape, but where is that point located? Can you describe its location somehow? Yeah.
On the y.
It's on the y-axis. Okay, so this is your y-intercept. It's on the y-axis, so y-intercept. So notice how if you think about it, okay, if you were to plot a point on the y-axis and you're folding the graph over the y-axis, would that point move? Would that point change? Wouldn't it stay on the crease, like where you're folding it? So there is no connected or related point for this one because it's on the line that you are using to fold the graph. All the other ones, though, are not. So when you fold them, they're going to land somewhere else. Okay, so all of these points on the left-hand side, okay, of the y-axis are somehow related to a point on the right-hand side of the y-axis. Notice how these are negative x values, so they're on the left. These are positive x values, so they're on the right. If we look at p of x, we can find that y-intercept, okay, x value of 0. So this point on the left-hand side is connected to a point on the right-hand side, specifically by having the same y value but the opposite x value. Do we see that same connection happening in p of x and q of x as well? Okay, we can identify y-intercept. So a point on the left is somehow connected to a point on the right. Okay, vice versa, yeah. Sure. Okay, so let's go ahead and write that connection down on page 101. Okay, we'll say the points on the left of the y-axis are related or connected, whatever word you want to use, to the points on the right of the y-axis by what? We said that the y value stays the same, but the x value becomes opposite. So we'll say by making the x value opposite. I guess since we're not mentioning the y value, we'll assume it's staying the same. Is that okay? Okay, by only making the x value opposite. Let's see if we can find kind of a similar connection for the rotational ones. So taking a look at the ordered pairs for the bottom chart, can we find a connection between those points? Yeah. Both the x and y values are opposite. Okay, so we'll go ahead and find those y-intercepts again. In R of x, we don't really have one listed, but we can determine where one would be. Okay, a y-intercept has an x value of 0. So notice how the points on the left-hand side of the y-axis are related to a point on the right-hand side, specifically by making each number opposite or negative of what it is. Okay, if we check out some of the other points in the other graphs, looks like it checks out the same way. Oops, this one. Do we see that pattern? Both values switch or become negative? Okay, so on page 101, we'll say the points on the left of the y-axis are related to the points on the right of the y-axis by making both x and y values opposite. Alright, so the reason that we're focusing on these two particular types of symmetries a little bit more closely is because we have a different way of phrasing them or classifying them. Instead of telling you that a graph has y-axis reflective symmetry, do you guys realize how long that phrase is, y-axis reflective symmetry? Instead of saying that, we can simply classify that type of graph as even. So instead of saying y-axis reflective symmetry, you can just say even. You see how much simpler that is? So what we're doing is we're classifying these two different symmetries a little bit more simply. So we're going to look at even functions versus odd. Okay, even functions are the y-axis symmetry relationship, and odd functions are the origin or rotational symmetry. Okay, so we're going to write down those relationships. Even functions is a graph that has y-axis reflective symmetry. Very similarly for odd function, we can say an odd function is a graph that has origin rotational symmetry. So instead of classifying the symmetry as y-axis reflective, origin rotational, you can simply say even or odd. Okay, it's a different way of classifying it. The way I remember it is odd begins with O and origin begins with O. So origin, odd, they're connected. That's how you can remember the classifying. So that's a kind of a graphical definition. Notice how we said in terms of a graph, that's how we can determine the type of even or oddness of the function. Let's go ahead and check out numerical. So numerical are in terms of numbers, like using those ordered pairs to help us out. We said at the top, okay, the y-axis symmetry, aka even functions, you keep the same y value, but you switch and make the x value opposite. Okay, so we're going to go ahead and say, maybe we'll use shorthanded here. If we have the point x comma y, then what other point do we know should be on the graph? Based off of the classification, yeah. Next, negative x comma y, good. Okay, let's go ahead and try an odd function. If we have the point x comma y, any point you want to pick on the graph, then what other point should also be on the graph? Or maybe in a table of values. You might not always have a graph. Maybe you have a table. What would that point look like based off of our kind of classification or observation from the top? Yeah?
Negative x, negative y.
Negative x, negative y. Perfect. Okay, so we're going to kind of step it up a little bit here in terms of the algebra or the notation. Okay, let's see if we can think about this in terms of functions, okay, equations. If I were to tell you the point x comma y is on the graph, how can we write that using a function notation, meaning f of something? Can we practice our function notation? Remember, an x value is representing an input and a y value is representing an output or an answer. So in function notation, which spot represents the input and which spot represents the output or answer? What do we normally see here? Is it f of x or f of y? X. Okay, so the input value, aka the x value, is normally placed inside the function, okay, inside those parentheses, and whenever you plug something in, you typically get something out. So if you plug in an x, you typically get out a y. That makes sense, right? We're used to that idea. So whenever you have the ordered pair x comma y, you could represent it in function notation. Okay, if you wanted to practice with numbers, for instance, if you had the ordered pair 3 comma 5, you could write that as f of 3 equals 5. We've seen that a little bit so far this year, or at least earlier. Okay, it's just getting a little, not difficult, but a little bit more advanced now because we're now working with variables instead of numbers. Okay, so we can represent this point using function notation. How might we represent this point using function notation? What represents the input and what represents the output? Yeah.
Negative x for the parentheses.
Uh-huh. And when you plug in negative x, you get out y. Perfect. Does that make sense? I know it's a little different notation, but I'm hoping the connection is okay for us. So what I want to try to do is merge these two ideas together, because we know if this point is on the graph, then so is this one. Okay, if you have y-axis, aka even symmetry. Do you notice how based off of these two function notations, they both equal y? So does it make sense to you that if they both equal y, then they must equal each other? Does that make sense? Okay, so instead of saying two separate equations, we can combine them together. If both of them equal y, then both function values equal each other. We could say f of x equals f of negative x. All right, so we're going to see this notation show up a little bit in the next few examples we do, Also maybe in a free response problem we're probably going to get to tomorrow. Okay, so whenever you see this function notation, this is cluing you in to even symmetry, aka y-axis. Because these two function values equaled each other, they both equaled y. That means the y value stayed the same, whereas the x values were opposite. Does that make sense? Okay, we're going to try to do the same thing for the odd values down below. Okay, so if this is our ordered pair, we should be able to write it in function notation. We'd have f of x equals y. We should also be able to write the other ordered pair. F of negative x equals negative y. Is that not bright enough for you guys? Can we see that? Okay, so we're going to try to merge these two together as well, but this one's a little bit trickier because notice how they don't necessarily equal each other, right? They equal, one of them is a y and one of them is a negative y. So let's think about this. If I were to say f of negative x equals negative y, do we know what y is? Can we use this other one to help us out? Isn't y f of x? Aren't those the same thing? You're used to saying f of x and y are the same thing. So instead of saying this function value is the opposite of y, we can say this function value is the opposite of f of x. Because after all, f of x and y mean the same thing. So here's a notation that's merging these two ordered pairs together, making a connection between the two. So this notation, notice how it's very similar to the other one. Okay, it's just slightly different. Notice how they both have an f of negative x, and they equal an f of x. It's just that one f of x is positive and the other f of x is negative. So they're very similar, but they're slightly different. So this one is cluing you into odd symmetry, that you're able to rotate the graph and it would line up on itself or be the same. Okay, so we're going to start seeing these notations a little bit more than just these ordered pairs, because notice how the notations come from the ordered pairs. Okay, let's see if we can just tackle one of them on the back. Okay, so analytically, meaning by hand, a function is even if the equation of the function f of negative x can be simplified to the same equation as the original. Okay, so if you take a look at this notation, this is telling us if you were to input, okay, plug in negative x into your equation, and you were to get out f of x, which is simply representing the original, then you know for sure you have an even function, meaning you can fold it across the y-axis. So let's make note of that. We're going to try to plug in negative x and see if we get the same equation. Very similar to the ones we did yesterday, right? Where we plugged in negative x sometimes, negative y sometimes, depending on the symmetry we were testing. Okay, very similar idea. All right, so we're going to test to see if this equation, this function, has y-axis symmetry. Can you fold it across the y-axis and it would line up on itself? So we're going to plug in negative x for all of the x's. And we're going to simplify it. We've got to see, do we get the same equation back? Do we get the original function back? So let's see, 3 times negative x is negative 3x. And from yesterday we saw negative x squared simplifies to positive x squared, right? Negative x times negative x. What about the absolute value of negative 3x? Yeah.
It would just be 3x.
That would just be 3x, right? Absolute values get rid of negatives. Do we get the same equation back? Okay, so even though we plugged in a negative x, okay, even though we're switching the x value, we're still getting out the same y value, the same function value. So opposite x, same y, that's indicative of a y-axis reflection graph. So therefore, we can classify it as even. No need to write y-axis reflective anymore. You can just write even. All right, let's try the next one. If we were to plug in negative x, would we get out the same y value, the same original equation? What about negative x to the fourth? We haven't seen that one yet. Negative x times negative x times negative x times negative x. Negative times negative times negative times negative. Yeah?
Would it just be x to the fourth?
It's x to the fourth, right. 4 negatives multiplied together is a positive value. 4 x's multiplied together is an x to the fourth. So we have a positive x to the fourth value, and there's that negative x squared again. So that's going to be positive as well. So we plug in the opposite x. Do we get out the same y, aka the same equation we started with? Yes. So this graph or function can also be classified as even. You have that y-axis symmetry. Does that make sense based off of this notation? You plug in negative x and you equal or get out f of x, that original one you're starting with. Does that make sense off the way it looks? I know the notation can be kind of a struggle because math can be like a different language with all these symbols. Okay, let's try to make a connection for this one. Okay, odd function. If we were to plug in negative x, what should we be anticipating to get out if it's an odd function, aka rotational? Instead of getting out the same equation, what do we want to get out in this case? Yeah.
The opposite.
The opposite of the original. Okay, we want everything to be opposite. So in this case, we're going to plug in negative x just like before and see if we get the opposite equation. Okay, isn't that the connection we said with odd functions or those origin rotational graphs? If you plug in negative x, you get out negative y, okay, the opposite y value. Okay, those were the ordered pairs that we discussed. So let's see if what's going to happen here. If we plug in negative x, let's see, we have negative 3x. What about negative x cubed? Negative x times negative x times negative x. Yeah.
It's just going to be negative x.
It's going to be a negative x cubed. Yep, negative times negative times negative is a negative. X times x times x is an x cubed. So take a look at what you get out. Do you have the exact same equation? If you did, it would be even. Or do you have the exact opposite? If you do, it would be odd. Is every term opposite of what you originally started with? Yeah, you see how they're negatives both in this case? So this would be an odd function or an odd graph. If you had the picture, you could rotate it upside down and it would be the exact same picture. All right, let's try the next one. Okay, 2 times negative x is a negative 2x. We have a minus negative x, which would change to a plus. And 2 times negative x is negative 2x, but the absolute value of negative 2x changes to positive. Okay, so take a look at what you have. Do you have the exact same equation? If you do, it's even. Do you have the exact opposite equation? If you do, it's odd. Is every term opposite of what you started with? Let's see, this first term here was a positive 2x. Is it now a negative 2x? That one's opposite. This next term was a negative x absolute value. Do we now have a positive x absolute value? Okay, so that one switched as well. So they're both opposite, which means this one would be odd. Are we doing okay so far? We're basically plugging in negative x. Okay, notice how that's what we did for both of them. We're just trying to see what do we get out. Do we get out the same equation or do we get out the exact opposite? Okay, let's check out some of them at the bottom. If we plug in negative x, see, negative x squared we've seen simplifies to a positive, and if we're adding a negative x, that's just the same as subtracting. So take a look at your result. When you plugged in negative x, did you get out exactly the same? Did you get out everything opposite? Or is it kind of a mixture? It's a mixture, right? It didn't the first term stay the same, but the second term was the opposite. So in this case, we have neither type of symmetry. So you cannot fold it across the y-axis because it's not exactly the same, but you can't rotate it either because you're not getting out the exact opposite. So in this case, we can simply say neither even or odd. Okay, it doesn't have either type of this symmetry, either rotating it or folding it across the y-axis. Let's check out the next one. We're going to plug in negative x and see what we get out. Do we get out the same equation? Do we get out the opposite equation? Or is it a mixture? What do you think? Exactly the same, exactly opposite, or neither? Yeah.
Neither.
Neither, right. Okay, so the first term was opposite. Notice how we have it as negative here where it was positive, but the second term started out positive and it stayed positive. So only one of the terms switched, not all of them. So again, we can say this is neither even or odd. We doing okay? Hanging in there? Okay, so big idea in this case. You're plugging in negative x and you're testing what are you getting out. Is it exactly the same? Is it exactly opposite? Or do you have that mixture, which means it's neither? Okay, we're going to save the free response for tomorrow, but we still have some time left. So maybe you guys want to start to try to practice some of those on page 105. Okay, you're determining whether if it's even, odd, or neither. So you got to plug in negative x and simplify it and see what do you get out. Exactly the same, exactly opposite, or that mixture. Yeah?
For that free response, are you having like partners?
No, this one we're going to do together tomorrow.
Oh.
It's not a free response day. This is just like a practice example. Okay?
Thank you.
Mm-hmm.